So this is day 3 of integration by parts. I want to show you one more cyclical integral, and then there's one final variation that I need to show you, and we'll be all set. So I'd like to take a look at the integral of e to the 3x cosine 2x dx. L-I-A-T-E. There's trig, there's something exponential. It's t, it's e, which is our signal that it's going to be one of those cyclical integrals. So my u is going to be the cosine of 2x, and my dv is going to be e to the 3x dx. Well, the derivative du of the cosine of 2x is negative sine 2x times 2, so negative 2 sine 2x dx. As for the integral, well, we would have to do a u substitution. Maybe I can kind of skip over that because u would be 3x, du is 3, dx, stick a 3 in and a 1/3 outside, and you're going to get 1/3 times the integral of e to the 3x. If you don't like that, here we go. Integral of e to the 3x dx. We can say u equals 3x, du equals 3 dx. So a 3 in and a 1/3 out. I'm going to get 1/3 times the integral of e to the u du, 1/3 e to the u. U times v minus the integral of v du is going to give me, remember with these cyclical ones, we do need to rewrite the original problem to get ready for our algebra step. The integral of e to the 3x cosine 2x dx equals, okay, so u times v, I'm going to say 1/3 e to the 3x cosine 2x minus the integral of this thing, and actually because that thing is going to end up being negative itself, I'm going to make it plus 2/3 times the integral of e to the 3x cosine e to the 3x sine 2x dx. I'm going to go do integration by parts again. L-I-A-T-E, I have something trig, and I have something exponential. So u is going to equal the sine of 2x. dv is going to equal e to the 3x dx. Derivative of sine 2x is cosine 2x times 2, so 2 cosine 2x. Stick a dx at the end. And the integral of e to the 3x, well, by the same logic I went through over here, I'm going to get a 1/3 e to the 3x, making use of a u substitution on that. U times v minus the integral of v du. I've got the integral of e to the 3x cosine 2x dx equals 1/3 e to the 3x cosine 2x plus 2/3 times, okay, so u times v will give me 1/3 e to the 3x sine 2x minus the integral of v du, so minus 2/3 times the integral of e to the 3x cosine 2x dx. I'm going to go and distribute the 2/3 over here to both of those pieces, and I'm going to get the integral of e to the 3x cosine 2x dx equals 1/3 e to the 3x cosine 2x plus 2/9 e to the 3x sine 2x minus 4/9 times the integral of e to the 3x cosine 2x dx. Now that I have the same thing inside this integral that I had in the original problem, I'm going to go and I'm going to move that from the right to the left, and I'm going to say plus 4/9 times the integral of e to the 3x cosine 2x dx plus 4/9 times the integral of e to the 3x cosine 2x dx let's see, I have one of those plus 4/9 of those. It's like 9/9 of those plus 4/9 of those things. I'm going to get 13/9 times the integral of e to the 3x cosine 2x dx. And on the other side, that equals 1/3 e to the 3x cosine 2x plus 2/9 e to the 3x sine 2x. Just about there. I am going to get rid of this 13/9 by multiplying both sides by the reciprocal, so by multiplying both sides by 9/13. Integral of e to the 3x cosine 2x dx equals, let's see, 9/13 times 1/3 e to the 3x cosine 2x plus 9/13 times 2/9 e to the 3x sine 2x. And I think at this point I'll start sticking that plus c at the end. Then I just need to do some simplifying here, and I'm going to get 3/13 e to the 3x cosine 2x plus 2/13 e to the 3x sine 2x plus a constant. So same ideas as last time, just a little bit messier because of the chain rule stuff we have to do on our u du stuff, and our u substitution stuff we had to do on our dv and our v stuff. One more variation that I need to show you, and I have two examples of this. What I'm now going to show you is called the chart method. And this is going to be useful when I have something in the form AT or AE when A has a large power. The chart method is going to be used when I have something that's algebraic and trig or algebraic and exponential. And in particular, I'm going to use it when A has a large power. Well, let me kind of show you why we're going to need this method. I want to go do the integral of x cubed e to the x dx. L-I-A-T-E, algebraic, exponential. Yep, it's definitely in one of the forms where I'm going to eventually use this chart method. But before I do this, let me just try doing normal integration by parts. U is x cubed. dv is e to the x dx. Doing derivatives now. du is 3x squared. V is e to the x. This times this minus the integral of that times that. I am going to get x cubed e to the x minus 3 times the integral of x squared e to the x. And this is going to be a pain because I'm going to have to do integration by parts again, and then again, and again, and eventually it'll end, but it's going to take a long time to do that. The whole point is initially I had an x cubed, now I've got an x squared. When you do integration by parts again, you're going to get an integral with an x in there, and you'll have to do integration by parts on that. Let me show you this new chart method. I'm going to make a table with 3 columns. My first column is going to alternate between positive and negative. My second column, I'm going to make my u. My third column, I'm going to make my dv. I'm going to put a plus over here. In my original problem, my u, we already said, was x cubed, and we said my dv was e to the x. So I'm going to write those things down. X cubed and e to the x dx. You know what, I'll skip the dx part. If I was doing normal integration by parts, I would then find the derivative of u, my du, and I would then find the integral of v. I'm going to do that over here. I'm going to make a chart where going down, I'm going to go find derivatives, and going down here, I'm going to find integrals. The derivative of x cubed is 3x squared. The integral of e to the x is e to the x. Let's stick a minus over here. More with the signs later. But the whole point is then what was my du over here and my v over here will now kind of become my u and dv in my new problem, and I'm just going to continue doing things. What you guys need to know is I'm going to continue doing derivatives until I can't anymore, and I'm going to continue doing integrals until, well, I run into a problem with the derivatives. My next row is going to be plus. It's going to be the derivative of 3x squared. It's going to be 6x. Over here, the integral of e to the x, e to the x. Next row, minus, because remember this first column is just going to alternate the signs. That's going to take care of the whole change the sign of the integral of v du thing in our integration by parts formula. I've got 6x and e to the x. Derivative of 6x is 6. Integral of e to the x is e to the x. Then I'm going to say plus. Derivative of 6 is 0. Well, that's actually kind of nice. That means I'm kind of done with my derivatives. And integral of e to the x is e to the x. How I'm going to piece all this together and get an answer. I'm going to take the sign and attach it to my u and multiply that by my first v, the integral of your initial dv. Then the sign with my u and my next v, the integral of that. And then these, and then those. I'm going to string all this stuff together, and I'm going to get positive x cubed e to the x. So I'm just going to say x cubed e to the x. Minus 3x squared e to the x. Plus 6x e to the x. Minus 6 e to the x. And then I'm basically done because every further derivative is just going to be 0. So I'm going to add a plus c to the end. This is the same thing I would have gotten if I wrote out the repeated integration by parts over and over and over again. But this is a shortcut we can use when we have a pretty high power on the algebraic part and would have to use integration by parts over and over. I want to show you one more of these. I'd like to take a look at the integral of x to the 5th sine 3x dx. L-I-A-T-E, I have A and I have T, which is the right form for me to be able to use this chart method, and I have a pretty high power on that algebraic part. So I'm going to set up my chart, plus or minus, my u, my dv. Plus, my first u is going to be x to the 5th. My first dv is the sine of 3x. Integrating this will require a u substitution. I'm not going to go through all that work. I'm just going to stick a 1/3 out front before each of these integrals as I do it. Next row, minus derivative of u is 5x to the 4th, and the integral is 1/3. Integral of sine is a negative cosine, so I'm going to say negative 1/3 cosine 3x. Next, plus. Derivative of 5x to the 4th is 20x to the 3rd. Integral of this thing, well, I'm going to leave that 1/3 out front. And I'm going to get another 1/3 from doing a u substitution on the cosine of 3x. And the integral of a cosine is a sine. So I'm going to say this, and I'm going to rewrite it as negative 1/9 sine 3x. Minus 60x squared. I'm going to get another 1/3 out front. Integral of sine is negative cosine, so the double negatives will turn that into a positive, and I'm going to get 1/27 cosine 3x. Plus, derivative here is 120x. Integral here, well, I'm going to get another 1/3 out front. That gives me 1/81. Integral of cosine is positive sine, so 1/81 times the sine of 3x. Minus derivative of 120x is 120. Integral of this, I've got another 1/3 I'm going to bring up front because of the u substitution, so 1/243. Integral of sine is negative cosine, so I'm going to say negative that, cosine plus 0. Oh, this tells me I'm going to stop. I'm going to bring another 1/3 out front. 1 over 729, it was negative, and the integral of cosine is a positive sign. So I've got this, and I'm done with the setup here. When I go to actually write out the answer, I take the sign, match it up with my u, and then match that up with my first v, the integral of your initial dv. So I'm going to fill in these little lines over here. I'm ready to go. First of all, positive x to the 5th times negative 1/3 cosine 3x, while a positive times a negative will give you a negative. And I'm going to say negative 1/3 x to the 5th cosine 3x. A negative times 5x to the 4th times negative 1/9 sine 3x, while a negative times a negative will give you a positive. And I'm going to get 5/9, the x to the 4th, 5/9 x to the 4th times the sine of 3x. A positive, a positive, a positive. I'm going to get plus 20/27 x cubed cosine 3x. A minus, a positive, a positive. I'm going to get minus 60 over 81. I bet I can simplify that. I'll do that in the next step. X squared times the sine of 3x. A positive, a negative. I'm going to get minus 120 over 243x cosine 3x. A negative, a negative will give me a positive, so positive 120 over 729 sine 3x. I'll stick a plus c at the end. Then I do have to just do a little bit of simplifying over here. I've got negative 1/3 x to the 5th cosine 3x plus 5/9 x to the 4th sine 3x plus 20/27, no simplifying yet, but the next part I'll have some simplifying to do, x cubed cosine 3x. 60 over 81, you can divide them both by 3 to give you minus 20 over 27 x squared sine 3x. Minus, well, I can divide again by 3. 120 divided by 3 is 40, and 243 divided by 3 is 81. And looks like I can divide by 3 one more time over here. 120 divided by 3 is 40. 729 divided by 3 is 243. And you're going to get that. And that's integration by parts with the chart method. Your homework will have a few chart problems, but also just some review of all the integration by parts we've been looking at. See you later.